Hi everyone, we are going to learn about live migration of virtual machines. The material covered here is primarily from two papers. One paper is on pre-copy live migration and another on post-copy live migration. So let's first look at what we mean by live VM migration. As we all know, virtual machines, they encapsulate an entire operating system and all of its applications. So for live migration, we want to transfer a running virtual machine with all its applications and the operating system state as it is to a target destination machine where it continues to run as if nothing happened. So the state of a virtual machine would consist of its memory, the CPU execution state, and the state of any I/O devices such as disk or network and so forth. So if you think about how a migration might work, we can think of it as having two migration manager processes that are outside of the virtual machine. And these migration manager processes talk to each other. They establish a TCP connection with each other. And the source machine, the migration manager, would map the memory contents and the execution state into its own address space, and then it would transfer this state over the TCP connection to the destination migration manager. There, the destination migration manager will receive the state and restore it back into a virtual machine at the destination. So, for example, to be more concrete, in Zen, for example, there is a process called ZenD that's responsible for a lot of different management operations, and one of those management operations happens to be live migration. Similarly, we have in KVM virtualization environment, there is a management process called QEMU, which is responsible for live migration among many of its other management functions. So why do we want to do live VM migration? So let's break this down into three parts. First, why do you want to migrate a VM? So sometimes people migrate VMs to do load balancing, like if you're in a large cluster environment where there are many virtual machines running, some physical machines may have a higher CPU load than other physical machines. So in this case, you might want to move some virtual machines over to the lightly loaded servers so that different servers are equally balanced. Sometimes you have to shut down certain physical machines for maintenance, for upgrades, and so forth, or because they're about to fail. So in these cases, you don't want the virtual machines to get affected, so you move them over to another physical machine so the old machine can be upgraded. And sometimes this is done for energy savings. For example, when you want to save power, then you might shut down some of the physical machines and keep others running. So in this case, before you shut down some physical machines, you move over the VMs to new machines. The second question is what's live about it? So as you might have guessed by now, we want to keep the applications that are inside the VM running. We don't want them to be terminated or shut down so that the user doesn't have to bring them back up again at the destination machine. Also, if there are network connections that are interacting with applications inside the VM, then you want to keep those network connections alive during the migration process. So, so we don't want these network connections to break if the VM moves to a new machine. So broadly speaking, we want the user to have a seamless experience, meaning that user doesn't realize that his or her VM has moved to a new machine, and that way you avoid any disruptions to the VM. This is really important in cloud computing environments where we all use virtual machines on this cloud, but we don't really care where those VMs are running. So if the VM gets migrated, we don't want to experience any disruption in whatever work we are doing. And finally, the question is, why do we want to migrate the whole virtual machine, that is the applications and the operating system state, which is quite a lot of data. Sometimes the VM's memory state could be several gigabytes. And if you also consider disk storage state, that can go into hundreds of gigabytes. So you might think an easier mechanism might be to just take individual applications or processes and move them over to a new virtual machine at the destination. So we could do process migration instead of VM migration. Well, people have thought about this in the past, but it turns out process migration is much harder because a lot of process state resides inside the operating system. And as a result, when you want to move a process, then you also need to extract all the process state from within the OS and install them in the new OS at the destination. So process migration turns out to be very tricky, and it's not always possible. There are many dependencies that cannot be migrated very easily. So a simpler approach is just to take an entire VM, which is like a self-encapsulated black box, self-contained black box, I would say, and move over the box to a new location as if nothing happened. So in summary, VM migration is much easier than process migration, much cleaner. All right. So when we talk about live migration, we have certain performance objectives, right? So when we say liveness means that user should experience least possible disruption, and that translates to a metric called downtime. Downtime is the amount of time for which a VM is not executing during the migration. Although we say it's live, there will be always some small amount of time, even if it's like just a few milliseconds, when the VM is not executing, where you have to stop the VM at the source machine and resume it at the destination machine. So this downtime in VM's execution has to be as small as possible. And we are talking about time scales of less than a few hundred milliseconds, right? Then the other metric is the total migration time should be low, which means that from the time you issue a migration command to the time it completes, where the VM is completely transferred to the destination and it's running at the destination without any dependencies at the source. So this entire total end-to-end migration time has to be reduced, and this is some different from downtime because you might issue a command, the VM may keep running, the downtime may occur somewhere in between, and then when the migration finally is complete, then it may be much later after the downtime. We will see how this works when we consider various migration approaches later. And then there's another requirement that if we are migrating a virtual machine, it's going to generate extra work on the on both the source and the destination machines, because you have to transfer the state over to another machine. And this extra activity in the system can affect other virtual machines that are running in both source and destination. So there may be interference with what other VMs are doing. For example, if some VMs are communicating over the network and we send the virtual machine's state over the same network, then that extra network traffic might end up adversely affecting other VMs that are not being migrated. So we want to reduce interference on other VMs. We want to minimize the network activity, which again is related to the VM interference problem that I mentioned, but also the fact that there are other machines in the network that are using the network fabric, and if we have a lot of VMs being migrated at the same time, it can congest the network. So the less data we can send to migrate a VM, the better it is. So downtime, reducing total migration time, minimizing interference within the source and destination machines, and minimizing interference over the entire network. So we can start by looking at some simple approaches to live migration. So if you think about a VM, what is a VM? There is memory contents of the virtual machine. There's the CPU execution state, the registers, program counter, stack pointer, and whatever the VM is doing at the particular instant. And then there's the disk state. All right. So for simplicity, we'll just assume that we are in a local area network environment, and that the storage is available over the network. So accessing storage is similar to communicating over the network for any other network activity. So this leaves us with mainly CPU, memory, and IO state, which here we'll primarily consider network for simplicity, right? So one way, if we don't want the, if we forget about liveness for a minute, then the simplest approach to migration would be to stop the VM, take a picture, take a snapshot of the VM, all of its state, move that snapshot over to the destination machine, and then resume that snapshot wherever it left off from the source, right? So, this is known as pure stop and copy, or you can also call it checkpoint and restore. We take a checkpoint or a snapshot of the VM at the source, transfer the checkpoint over to destination, and restart it there. So as you can imagine, the checkpoint contains the entire memory contents of the VM at the source, which is like the biggest component of the entire VM's state. CPU and IO state are relatively small. So much of the time taken to migrate the VM using this pure stop and copy approach is the time to transfer the memory contents from the source to the destination machine. So since we freeze the VM at the very beginning, what that means is that the total migration time is going to be equal to the downtime, meaning that for the entire duration that the memory is being transferred, the VM is not running. So that's a lot of disruption time. So if a user is using the VM and his virtual machine is down for say 30 seconds or a minute or a few minutes, then they're going to notice it. They're going to complain, right? And we don't want users to complain. So what are we going to do? Well, but there is an advantage to this, which is that the total migration time from the start to the finish is going to be as little as you can get, because all you're doing during this entire duration for pure stop and copy is just migrating the VM state and nothing else, right? So there's nothing to slow down the migration. So we could kind of flip this approach around and say we could have something called pure demand paging. What that means is that we freeze the VM at the source first, and then we copy the minimal execution state that includes ideally the CPU state, program counter, registers, and so on, and some minimal amount of memory that cannot be paged, that cannot be swapped. So non-pageable memory. So if we take this minimal execution state and move it to the destination, leave everything else behind at the source, and with this minimal execution state, we start the VM at the destination. All right. So since we have the basic CPU execution state, the VM will start. It will try to start executing instructions. It will try to start accessing its memory. But the memory contents, most of the memory contents, we have left it behind. So when the memory contents are accessed at the destination, they will generate a page fault. When a page fault is generated, then our migration manager at the destination would say, hey, wait a minute, I haven't brought this memory in, let me go back and ask the source to give me that memory, right? So every page fault, you ask the source, bring the page back to the destination, the faulted page, and then let it execute further, and then another page fault, bring another page back to the destination from the source, and you keep doing this till forever pretty much, because initially you will have a lot of page faults, slowly you will have a working set at the destination and enough to keep going, but still there will be some memory left behind at the source because we haven't brought in everything. The VM may not have faulted on all the pages. Okay, so it's so the VM starts executing at the destination right away with this pure demand paging approach, but it will be really very, very slow at the beginning because you have to fault in each and every page, and so the downtime is really small, right? Because from the time you freeze the VM to restart the VM as a destination, it's a very small amount of time. But then the total migration time is indefinite. Basically, the VM migration never completes because there is always some memory left behind at the source. So that's not good either, right? So pure stop and copy and pure demand paging are two extreme ends of the spectrum. Okay, and we want to do something better. Okay, and that's where we go to the next two approaches: pre-copy and post-copy. So let's first look at the pre-copy migration approach. So the idea here is that we're going to copy the memory of the VM from source to destination. While the memory is being copied, we want to keep the VM running at the source. Okay, so that's why it's called pre-copy. Copy the memory first and then migrate the VM. Pre-copy. Okay, so uh, the steps are as shown. So we don't freeze the VM at the source. We let the VM continue to run. And as it is running, we start copying the memory pages one by one from source to destination. So the migration manager at the source will take a page, send it to the destination, then take another page, send it to the destination, and so on till it's done with all the pages. Okay, so by the time it started from the first page and finished at the last page, what has happened? In the meantime, the VM has been running in the background, and when the VM runs in the background, what does it do? It reads from memory and writes to memory. Okay, so by the time we have finished copying the first time, the some pages that we had previously copied would have been dirtied or written by the VM. Okay, so now we have to go back and find out which pages were dirtied while we were doing the first round of copy, and then in the second round we copy those dirtied pages over. Okay, so it's and the same thing during the second round when we are copying the dirtied pages, the VM is still running. Then at the end of the second round, we have to go back, identify which pages were dirtied in the second round, and then we have to copy those pages over in the third round, and we keep doing that over and over and over many rounds. Okay, so our hope is that as we go from the first round to the second round to the third round, we have to copy fewer and fewer and fewer pages. Okay, so because we are hoping that the VM will dirty fewer and fewer pages upon every subsequent round. And if our assumption is true, then at some point there will be no dirty pages left or very few dirty pages left. And at that point, we can afford to freeze the VM, stop the VM, and copy any remaining dirty pages, any few remaining dirty pages, and then move the CPU state and IO state over to destination. And at the destination, now the destination memory migration manager has all the necessary VM state. It can restore this VM state and start the VM at the destination. Okay, so this is pre-copy migration. Now, what if our assumption, we made an assumption that in every subsequent round we'll have fewer and fewer dirty pages. So what if this assumption is not true? What if the VM writes a lot to its memory, writes to a lot of pages? So in every subsequent round, we have a lot of dirty pages to copy. Sometimes there will be, more dirty pages in the next round than in the previous round. So in this case, we would never converge. We'd never get to a point where we have very few dirty pages where we can pause the VM and start downtime. So this is a problem with pre-copy. So you get a very small downtime because you have very few dirty pages. If everything works well, you will get very few dirty pages and very small CPU and IO state to transfer during downtime. But if our assumption is wrong, then we will never get to a point where we get a small downtime. There's also another question that we did not answer in this discussion of pre-copy. The question is, how do we track the dirtied pages. Remember that if in every subsequent round we copy over the pages, we transfer the pages which were dirtied in the previous round. But how do we know which pages were copied in the previous round? So we use an approach that we had learned earlier in super pages, if you remember. So the idea was that we would mark all the pages of the VM or the interested region of the memory as read-only, and if the VM writes to any page, the write operation would generate a write fault. And whenever a write fault is generated, we can note down which page was being dirtied by the VM, and then we could mark the page read write to allow the write to proceed. And this way, at the end of each round, we would know exactly which pages were dirtied in that round, which could then be transferred in the next round. But before we start the next round, we have to mark all the pages of the VM as read-only again, so that we can track dirtied pages for the next round. Okay, so this is kind of a expensive operation, because write operations will all now result in a write fault, which would then trap into the hypervisor, and the hypervisor would then note down, it would keep a dirty bitmap to keep track of which pages are being dirtied. Okay, so as long as writes are infrequent, this overhead is somewhat acceptable. But if a VM is write intensive and we are using precopy, then every write operation, every first write operation on a page during any precopy round will generate a write fault, and that can add up to a significant overhead. So there are many optimizations to make precopy work better. None of them are completely solving the problem, but they can help. One is that to avoid interference with other VMs that are running on the same machine, we could limit the bandwidth that is used by the VM migration, so that this way, let's say you have a 10 gig network interface, and you maybe assign only 1 gigabit per second to the migration, and the rest of the 9 gigs could be used by other applications. So this way it will take you longer to transfer the VM out, but the impact on other VMs running on the same machine would be less. The second optimization deals with write intensive applications. So if we find that a particular process inside the VM is writing a lot to the memory, it's dirtying memory at a very fast rate. So if we can somehow tell the guest operating system, pause that process, stop it temporarily so that I can complete my migration. So that way, so of course this requires para virtualization. You have to have the guest's cooperation for this to work. But if you can pause the process that are dirtying memory, and then finish your migration and then restart those pause process, then it can kind of solve this problem. But then it's not as live anymore, because during the migration those write intensive applications are not running, right? So it's almost as good as pure stop and copy. And then another optimization is to reduce the amount of network traffic. So if you look inside the memory of any operating system, a lot of the memory is page cache, where you just keep pages around that were used in the past and hoping that they may be used in the near future. Or a lot of them is just free memory, right? That will be allocated to some process. So during VM migration, all of these pages are being transferred, and we don't need to transfer the page cache and free memory pages. So if we can identify these and if we can exclude them from migration, then we only migrate the pages that are really needed at the destination. So that's another optimization that one can implement. Okay, but the basic problem that write intensive applications would cause pre-copy migration to go on for very long. And even if we, in the pre-copy migration, even if at some arbitrary point we say, okay, we're going to initiate downtime, that downtime is still going to be very large. So write intensive applications need a better solution. Okay, that's where post copy migration comes in. As the name suggests, post copy, meaning that we're going to copy the memory after the CPU and IO execution state has been transferred. just like what we did with pure demand paging a couple of slides ago, right? So here the idea is when you want to migrate, you pause the VM right away, okay, and then you transfer the CPU and I/O execution state to the destination, and you resume the VM even though there is no memory available for the no memory has been transferred for the VM. And by doing this, we will, as we discussed for pure demand paging case, now as the VM executes, it will start generating page faults, and then the source machine can go back to the host destination machine can go back to the source machine and request those pages back, right? But if we just did that, that's going to be very slow. The migration will never complete. So that's pure demand paging, right? So we want to do better than that. We want the migration to complete. So the source machine doesn't have to sit there passively waiting for page fault requests. Rather, it can actively push the pages over to the destination. So it can, as the VM is executing at the destination, source machine can actively send pages over the TCP connection to the destination. So hopefully most of the pages would reach the destination even before the VM faults on those pages, and that way, you get very low downtime because you pause and resume the VM almost immediately, and you get a very deterministic total migration time, because unlike for pre-copy, if a page was dirtied, you had to send it again and again and again. But in the post-copy case, you don't have to send pages many times. Every page goes over the network only once, right? So this is a really clean solution to the write-intensive workload problem that we discussed earlier. But what's the catch? As with any other migration, nothing comes for free. So the catch here is twofold. One is that as soon as the VM is migrated to the destination, when it starts executing, it's going to be really slow, because a lot of initial few memory accesses are going to be page faults, and those faults would have to be resolved by asking the source, okay, assuming that those pages haven't already been sent to the destination. And soon enough, the working set will be there and the VM will start running full speed. The second, probably more serious problem with post-copy is that the state of the VM, if you think about it, the state of the VM is now split across two machines. So there is the CPU execution state at the destination and more up-to-date memory content at the destination. But then there's also some remaining memory at the source that hasn't yet been sent to the destination, right? So because the VM state is split across two machines, if anything goes wrong, let's say the destination machine fails, all right, you don't have the up-to-date state of at the source machine to recover the VM. Or let's say the source machine fails, then the destination doesn't have all the memory it needs because the migration hasn't completed. So if there is a failure during post copy, then you lose the VM, right? Or the network might fail, in which case the VM can't proceed. Source and destination can't communicate. If pre-copy, on the other hand, is slightly better, if the destination fails or the network fails, you can just cancel the migration. The source still has the most up-to-date state in pre-copy, and the VM can still continue executing. So here's another metric that we didn't list earlier, which is reliability, right? Which is if anything goes wrong during VM migration, can we still recover the VM from most consistent state? In this case, it turns out pre-copy is better than post-copy in terms of reliability, right? But post-copy gives very deterministic performance for whether the workload is read intensive or write intensive. It doesn't care. And you could say, well, we could combine the benefits of both pre and post copy, but then when you combine them, you also combine their drawbacks. So in this case, you could do one round of pre-copy, and then and during that one pre-copy round, the VM continues running. It dirties some pages, right? And then if you want, you can do a few more rounds if you have a lot of dirty pages. Then you start initiating downtime. In the downtime, you don't transfer any memory. At the destination, you resume the VM, and then any dirtied pages can be faulted in and or actively pushed using post copy from the source. So so we're kind of combining pre-copy and post-copy, and if you this way we can fix the number of pre-copy rounds at the source, and post-copy of course is deterministic, and even if the workload is write intensive, we will finish the whole migration within a fixed amount of time, right? And hopefully, if the workload is read intensive, then we just use only pre-copy rounds, and there may be no need for a post-copy. So the hybrid approach is kind of attractive, but then because there's a post-copy component involved, it's not as reliable, and because there's a pre-copy component involved, the migration may take we may do a few pre-copy rounds, and we may still find we have a lot of dirty pages, and we may end up having pushing all the work to the post-copy phase. So it's an interesting design point for live migration. Okay, so a big part of liveness for live migration is that the users who are interacting with the VM, they should not see any disruption in their work. So if you have a network connection open with the virtual machine, you want the network connection to stay alive, right? So what that means is if you had the network connection state has to migrate with the VM. It's not a big problem because all the state of network protocol state is encapsulated within the VM inside the guest OS. Since we are migrating the OS state also, uh, so the network connections would automatically transfer over. Okay. So the IP address, MAC address, port number, all the open TCP connections, everything would just migrate over automatically. We don't have to worry, right? Uh, all that the VM needs as a destination is a new virtual network interface, and then based on that, which it can start using as if nothing had happened. The only problem is that the VM has moved from one physical machine to another physical machine, and the network switches, the network fabric that connect these machines to the rest of the network, they have to learn that the VM has moved. Specifically, there is a specific protocol called backward learning or reverse learning that is employed by these switches. If you have taken a course in network, you will learn more about the spanning tree protocol and backward learning. So what this backward learning does is it looks at the packets that are going to a particular destination, and then based on where the destination is sending its packet, it would then backward learning technique would then send the packets to the same port. Uh, so when a VM moves from one physical machine to another, these intermediate switches they look at the VM as if it's another machine, another physical machine, right? So the VM moves, then the switches have to learn what is the new location of this machine. Has it moved over the network? And this learning phase is a little expensive, and it takes some time. Like typically it might take 30 seconds or so if you just leave it by itself, and during those 30 seconds the VM may not be getting any packets, right? So we may have a sub 100 millisecond downtime as far as the migration is concerned, but as far as the network connections are concerned, they may not get any packets for 30 seconds. So it's as good as the VM being offline. So that's not good. So there is a solution to that also. So what the VM does is, the migration manager does is, it would send an unsolicited ARP reply. ARP stands for Address Resolution Protocol, and ARP is used in ICMP echo messages. So if you ever used the ping command tool to probe the liveness of a machine, and see whether it's alive, you get back a reply, right? Uh, so this tool uses the ARP commands, ARP request and ARP reply. So the migration manager will send out an ARP reply even though nobody has asked its location. It will send out an ARP reply over the network. ARP reply, as it propagates through the network, all the switches in the network would learn where is the new location of the VM. So it speeds up the relearning process in the network switches from like 30 seconds, say, to just a few milliseconds. Okay. Um, so the other question is, what if you're migrating the VM not within a same subnet, same IP subnet, but across subnets from, say, over a wide area network, say from East Coast to West Coast of the United States, or from United States to Europe, right? That's, you might want to do something like that, and in such cases, you are basically, the VM gets a new IP address in a new subnet, and now the network identity of the VM changes. So in this case, you may have to use more advanced techniques like tunneling through VPN or some such technique to make sure that any network traffic that goes to the source subnet is then redirected to the target subnet where the VM now actually resides. And then we didn't talk about storage migration. For the LAN case, we sort of just assumed that the storage is accessible over the local area network, say network file system or network block device, and so on. So that kind of simplified the problem. Then storage migration basically became the same problem as network state migration, right? But for wide area network, again, accessing the storage over a common network device is not possible across wide area. So we may have to transfer the disk image, the virtual disk image of the VM along with the VM itself. Now, disk images are much larger. They may be hundreds of gigabytes or terabytes, and transferring that will take time, and it's also a lot of data, right? So again, the techniques that we discussed earlier for memory, pre-copy and post-copy, can also be used for disk images. And then you can also apply additional optimizations like compression or deduplication to to reduce the amount of storage data that's sent over. But this is again live migration over wide area networks, again, an important problem, because in disaster situations, for example, a hurricane is going to flood your data center in New York City or Florida, and you want to move everything over to Arizona. This has happened before. Like there was a Sandy hurricane where a few years ago, and all the financial hub centers, they were trying to move over their workload to Arizona, right, where they don't get floods. So that's a wide area network migration, and in those cases you also have to move over the virtual disk image. And there's another interesting design point. It's called self-migration. Here, everything we've discussed so far requires a migration manager, the hypervisor, to be aware that the VM is being migrated. But sometimes you want a VM may want to migrate itself without help from the hypervisor. So the live migration paper by Christopher Clark and co-authors, it talks about the self-migration. They even implemented a self-migration technique where the guest OS migrates a copy of its own memory over to a destination node. At the destination, there's a VM waiting to receive the state, and basically it faithfully applies every page of memory over to itself. And since it's supposed to be live, then there are some additional transaction commit like mechanisms involved, where since the VM is migrating itself, you want to migrate all the state, but then the part that is doing the migration itself is changing the state of the VM. So you need a two-state checkpoint and copy type mechanism. So we'll leave the details out. If you're interested, feel free to read the paper. And then there are a couple of other techniques that we didn't discuss in class, but I put in the slides here because these are still interesting techniques. Sometimes you want the source. You want to migrate a VM from source machine to destination machine, but let's say the destination machine is too slow in receiving, and the source machine is in a hurry to offload the VM. So what it can do is it can kind of push the VM state out to whoever in the network is willing to receive it, right? So in the network there may be a lot of intermediate hosts, here I1, I2 up to IN, And since this destination machine is slow, so the source will say, okay, I'm going to just scatter the VM over to all these intermediate nodes, right? And then the destination machine can gather the VM state at a later time at its own pace. So this way, if you have to quickly deprovision a machine, deprovision meaning turn off a machine for maintenance or whatever, then in this case you can scatter the VM into other nodes in the network, and then the destination could pick it up more slowly. Okay, um, and, and another interesting case, and this is actually more common uh, than a single VM migration, which is multi-VM migration, multiple VM migration. So you have a bunch of machines running in a machine, a physical machine, and then you want to migrate them all out at the same time. Since every VM is large, if you start to push them all out at the same time, it's going to choke the network, and this is a very common problem. VM migration starts, then network gets congested, nothing else can happen. So if you're not careful, right? Uh, so this is a very important problem. So it turns out, if you look at the problem carefully, a lot of these VMs are very identical. Maybe they are all running Linux, or they're all running Windows. They have similar code, similar applications, right? And a lot of the memory pages are just zeros, filled with zeros, right? So a lot of these pages are identical. They have same content. So why do we transfer them many times over the network? So if we can identify which pages are identical, then we can just transfer one copy of every page and then make multiple copies of it at the destination machine, right? So this is called gang migration or multiple VM migration, and the process of identifying identical pages that have identical content is called deduplication. Deduplication is also used extensively in storage systems where you want to reduce the size of the file stored in your disk or storage system. You can deduplicate the files. Uh, so deduplication is expensive. There is a trade-off involved because you have to compare pages. The naive way is to take two pages and compare them byte by byte to see if the content is the same. And if you're comparing hundreds of gigabytes of memory pages this way, it's going to consume a lot of CPU cycles, so not very efficient. A cheaper way is to use checksums. So you can take the checksum hash value and then just compare the hash values together. Okay, and if you do it in a smart way, then it can save a lot of computation power. All right, so that's another optimization for multi-VM migration. Okay, so that's all we have. There's this topic has many other interesting angles. So feel free to explore more and ask if you have any more questions.